Hello friends, welcome back to Quantum Quandary. Today we're going to be discussing the Doppler effect. First of all, we're going to be looking at a source that emits radial wave fronts. Okay. And we're going to be seeing how an observer O, the source is stationary, and the observer O is moving at a velocity v, speed v, whatever, in the radial direction. Now, in our first analysis, it's going to be moving towards the source. So, we're going to mark this distance between two wavefronts as lambda. And we know that lambda is equal to the velocity of the wave, which is going to be c, over the frequency. I'm going to mark that with an f, okay? So the wavelength is proportional to the speed of the light, or of the wave, and inversely proportional to the frequency. And we also know that the frequency is just 1 over the period. So a period is how much it takes for the wave to come from one peak to the other. A period is very similar to the wavelength. I mean, if we look, then the wavelength is just ct, right? This is kind of similar to x equals vt, right? It's kind of the analogy for the wave. And indeed, we're going to be using this. So if we consider that our observer O is reached by the first peak of the wave at t equals 0, okay? And okay, let's consider velocity over there. I just find it to be simpler to visualize for the first time. So if our observer then starts moving at the velocity v, then after some time, it'll be x away, right? And we know this time. This time is t equals x over v, right? Or x is equal to vt. So after some time, it will be x units away. And the wave will have also progressed. So we are interested when the observer, let me just figure out how to draw this. When the observer moves, we're going to be considering v less than c, okay? Of course, if we didn't have that, then the wave fronts would never reach the object, the observer. So after some time, we're going to have we want the second wavefront to reach, right? And this is we're gonna mark it at t equals t prime. We want the second one to reach. Now the wave has since traveled ct prime, right? The wavefront had to travel ct prime. And the point, the observer, has traveled vt prime. Okay. And the wave had to cover the distance lambda. So what we have is, here's the wave front that already reached us at t equals 0. So let's call this wave front 1. So this is wave front 1, this is wave front 2. And these two guys are away by lambda. Okay. These two guys are away by lambda. So he had to, the number 2 one had to catch up by lambda, and then also by vt prime. So that means that ct prime is equal to vt prime plus lambda, okay? We can just express t prime by this analogy. So we can say that lambda prime is ct prime. So then this is lambda prime. That's equal to v over c lambda prime. You see what I did there? Plus lambda. And now all we need to do is express, I'm going to write that here. We express that lambda prime is equal to 1 minus v over c in the denominator times lambda. Like this. So, lambda prime, we know that this is something that's between 0 and 1. Okay? Because we said that v is less than c. So this is something between 0 and 1. And that means that lambda prime is going to be lambda times something that's greater than 1, right? So we've got 1 over 1 minus something between 0 and 1. So lambda prime is going to be greater than or equal to lambda equal when v is equal to 0. Okay, so we've got a stretching of the wavelength when an object is moving away from the source. It makes sense, right? So what we have is when we have a stationary source and an object which is moving it away at v, we have that lambda prime is greater than lambda, and we have that f prime is then, by this simple formula, it's less than f, and this is what's called a redshift, okay? A redshift. So objects that are moving away from the source, or conversely by relativity, if the source is moving away from the object, the observer, we experience a redshift. We see these frequencies as smaller than they really are. Okay, so that's the redshift. And conversely, for the stationary source and the object moving towards the source at velocity v, we have that the wavefront CT prime has to cover a distance of lambda minus VT prime because the object is coming closer, right? So the object kind of goes towards the front, the wavefront. And from here, we do our conversion to lambda prime is lambda minus V over C lambda prime. And we get that lambda prime is 1 over 1 plus V over C lambda. Again, V is less than C. So in the cases where V is greater than C, well, actually, in this case, it doesn't matter, does it? In this case, it doesn't matter. In the other case where you leave, it doesn't matter. It does matter because the wave is never going to catch up, the second wavefront. But here, yeah, it does not matter. It does not matter. Lambda prime never becomes negative because, well, V is always greater than 0. If it wasn't, then it would be going in the other direction. Well, technically, we could cover both of these cases and then not limit V greater than 0, but yeah. V can be greater than C here because we're moving toward the wave, so it doesn't matter. And even regardless of whether V is less or equal to or greater than C, lambda prime will always be less than lambda because, you know, we're dividing by something greater than 1, so that means that f prime is greater than f, and this is why when something is coming closer to you, it looks like it has a bigger frequency than it is. That's why we joke that every light is a green light if you move fast enough. Yeah. So, yeah, that's about it for the, radial direction of the Doppler effect. Next time we can do the non-radial directions, and I'm hoping to do some relativistic Doppler effect as well. Okay. Thank you guys for watching. Bye-bye.